All right, let's get started with this SI sheet. First, we have some review for the final exam, some stuff from first semester, and I guess the second one is from second semester. But let's start with the first one. I'm going to redraw the molecule since it's kind of small how it's written currently. So we have to predict the reagents that would give this alcohol starting from this alkene. So if we look at the alkene, and if I label that 1 and 2 and label these carbons 1 and 2, you'll see that we add an alcohol to the least substituted alkene. So we need a reaction that's going to add an alcohol to the least substituted alkene, add it to carbon 2, which is the least substituted. If we look at A, H2O and peroxides, that's not a reaction we learned, so we can just throw that out. H2O and so this is just hydrolysis that's going to combine to create H3O plus. If you would do this, what would happen is you would create a carbocation on carbon 1, and then that would rearrange to the carbon to the left. So that would make an alcohol add there to the tertiary carbon and not carbon 2. So it can't be that one. B2H6 followed by H2O2 and NaOH. So B2H6, and then because it says followed by, that means that this is the second step. We've definitely seen this reaction. You might not recognize B2H6, but if you would divide that by 2, then it's BH3, and that's a reaction we've seen before. And that reaction does indeed put an alcohol on the least substituted. So it's going to be that one. Let's still go over what the last one would be. The last one we also saw last semester, mercury diacetate, and then with water, and then followed by sodium borohydride. That reaction we've seen, but that would put an alcohol on the most substituted part of the alkene, not least. So should be the C B2H6 because that's basically BH3. Just two equivalents of the BH3. All right, next one. This one is from the second semester of OChem. So I'm going to redraw the molecule we're starting with. So that right there. Okay, so the first step is we have ethylene glycol, which looks like this, and it's acidic conditions. That's what H plus means. So I'm just going to write acidic conditions. If you remember correctly, ethylene glycol, when used with carbonyls, serves as a protecting group. So the result of the first arrow is going to put that protecting group on. Put the ethylene glycol on instead of the carbonyl to protect that carbonyl spot. So that would be the first arrow. The second arrow, we have an alkyne, which has a negative charge because it has this ionic bond. And because it has a negative charge, it's going to be a strong nucleophile that's going to perform an SN2 reaction to displace the bromine. Because this is our nucleophile and our electrophile is this carbon, since there is a dipole going towards the bromine, making this have a partial positive. So that would be the result of the second step, and we still have our protecting group on. So now we just put on the alkene, and then the last step is just hydrolysis. And if you remember correctly, hydrolysis is how you take off the protecting group and re-put whatever carbonyl you had to begin with. And just realize this should be hydrogens. So hydrolysis, when you have a protecting group, is just going to take it off and re-put the carbonyl there. So because of that, this is our final molecule, which is option D. All right, so that's it for the final review prep. Now we'll get back to focusing on this test. First, we have to show the mechanism of this ring closure using the enolate mechanism, given we're in the enolate chapter. First, let's just number the carbons. I'm going to use a different color. And let's try to figure out where in the molecule each of those carbons are. So this carbonyl is either going to be carbons 1 or 6. It doesn't matter. I'm just going to put that as 1 because that feels better in my head. 1 is attached to 2. And now we have to figure out whether 2 or so 2 is attached to 3. Now we have to figure out if this is 3 or if the top is 3. And I think one really easy way to go about it is how many hydrogens does this carbon have and how many hydrogens does carbon 3 have? Carbon 3 has 3 hydrogens. Or not, carbon 3 has 2 hydrogens. Oops. And this carbon up here has 2 hydrogens, where this one has 1. So because of that, this top one is probably also carbon 3. And then 3 is attached to carbon 4, which is attached to 5, which is attached to 6. And this makes sense that this is carbon 6 because carbon 6 has 1 hydrogen on the product in the reactants and has 1 hydrogen on the products. So that lines up. And also, we know that in this chapter with enolates, when you use heat, you're going to create an alkene and remove an alcohol group eventually. So this is probably going to be turned into alcohol. And then with the presence of heat, it's going to be turned to an alkene. So that's why it makes sense that carbon 6 is located right there for all those reasons, just listed. All right, so now that we have the numbering, let's work on doing the reaction. So always the first step in these enolate reactions is forming the enolate. So we're going to take the alpha proton, which we're going to take carbon 2's alpha proton. We know we should probably take carbon 2's alpha proton because we want to form the enolate on this side because whatever side the enolate is formed, that carbonyl is going to stay in the product. The carbon 6 enolate, the carbon 6 carbonyl in the product was removed, so we probably shouldn't form the enolate on that side. So we're going to take the alpha proton and then push the electrons onto the carbon and then push the carbonyl electrons onto the oxygen. And that gives us our enolate. So let's draw the result of that. And then I'm going to number my carbons. And I'm just realizing that I didn't want this double bond to be between 5 and 6. I wanted it to be between 2 and 6. So I'm gonna redraw this molecule. And then on the worksheet I send out, I'll make sure that's the correct molecule. It should be between these carbons because we want the most substituted alkene. This alkene is more substituted than the other one. So I'll also renumber that as well then. 1, 2. All right, there we go. Now we can continue. All right, so now we have our enolate. Enolates are strong nucleophiles. They're strong nucleophiles because they have a negative charge. We are taught in Mullen's organic chemistry that strong nucleophiles are going to have a negative charge. So it's not the oxygen that's going to act as the nucleophile, but rather it's going to be the carbon. So we can drop the electrons down, and then we're going to push the electrons on the carbon 2, and then we need to attack something. We're going to attack another carbonyl because that's what happens in the enolate chapter, unless it's attacking a haloalkane, but we haven't learned that yet. And carbon 2, it's going to attack carbon 6, and we know that because, excuse me, we want carbon 2 and carbon 6 to form in the products. And coincidentally enough, carbon 6 has an electrophile, so the carbonyl. So we use our nucleophile to attack this electrophile over here, push the electrons onto oxygen. So this is going to form our ring then. And let's number the carbons. I'll do it there. And on carbon 6, we should have now an oxygen with a negative charge. We can use just water to protonate that. since we don't have an acid quench, and then just draw the result of that. And number the carbons. So where we are right here, we have a, we just added an alcohol on to the molecule. If the reaction wasn't heated, so if I scroll that out, then this would be the final product, but because it's heated, we have to continue on. So if we look at the products, or if we look at where we are and the products and look at the differences between the two, you'll see that in where we are, we have an alcohol, and in the products, there's no alcohol there. Instead, there's an alkene. And then if you notice, carbon-2 here has 1 hydrogen, and in the products, it has 0 hydrogens. So that is how we're going to eliminate the alcohol. We want to eliminate, or we want to take this hydrogen and eventually kick it down to form the alkene and get rid of the alcohol. Not going to happen all in one step, but that's what we want to happen. So we are going to take that hydrogen first. That does indeed occur first. We can use hydroxide because we just made hydroxide right here to take that hydrogen. And I wish we could just draw the arrow to put to create the alkene and then kick this off. That'd be nice and easy. But unfortunately, that's not what happens. We're going to push the electrons onto that nearby carbon and then push the carbonyl electrons onto oxygen. So that's going to happen first. Now we have another enolate where we are. Like this, and this oxygen is a negative charge. And now we can kick off this alcohol. This oxygen is going to kick the electrons down. And then we are going to move the alkene to where we want it in the products in between these two carbons, and then kick off the alcohol. And that's going to be our mechanism there. All right, the next one, we need to do acid catalyzed enolate addition. So anytime you're in acidic conditions, we are going to protonate the carbonyl oxygen first. So let's do that. So now we have a protonated carbonyl oxygen. So now we're not going to form an enolate by technicality because an enolate has a negative charge, and we're in acidic conditions, negative charges cannot be formed. So rather, we're going to form an enol here by taking the alpha proton with water and then pushing the electrons to create the alkene and then getting rid of the positive charge on the oxygen. So now we have made our enol. And we need to form a carbon-carbon bond. We need to form a carbon-carbon bond between the alpha carbon, and we need this to attack another version of the starting material. We know we need to attack another version of the starting material because if we look at the product, you'll see that this looks a lot like the starting material, so those carbons are probably all the same. And then where this double bond is, that is going to be the carbonyl of another version of the starting material. And we know that because if you continue looking down the molecule, you'll see we have this tert-butyl group here. And in the starting material, there's also a tert-butyl group here. So we're going to, with that, we know we are going to use another version of the starting material in the next step. So we want this alpha carbon to attack the carbonyl, but if we did that, that created a negative charge on the oxygen, and we're in acidic conditions, so that can't happen. So what's going to happen before this gets attacked is that this oxygen is going to be protonated, kind of in the same step that we showed, literally very similar to the first step that we did. So I'm going to just draw another arrow going that way. Excuse me. And now with a stronger electrophile, because there's a positive charge, we can have a weak nucleophile like an enol attack the carbonyl oxygen. Have the alkene act as the nucleophile. So Let's draw the result of that. So this group I'm drawing on top was the nucleophile. And then the group I'm going to draw on bottom was the electrophile. So make sure I draw this right. There we go, like this. So the next step would be to get rid of the positive charge, so deprotonate. And if the reaction wasn't heated, this would be our final product right here. But the reaction's heated. So what heating does is it's going to form an alkene where the new alcohol is. So that would be right here. So in order to form the alkene, we need this alcohol to leave. Alcohol is not a good leaving group though. So first we're going to need to protonate it to make it a better leaving group. I lied. That's gonna happen, but first we're gonna work on deprotonating this hydrogen. Because if you look in the products, that carbon has 0 hydrogens, right? Where we are currently, it has 1. So we're gonna work on deprotonating this first. However, we can't deprotonate it right away because if we deprotonated it right away and push the electrons here, that would create a negative charge on the oxygen. So first we have to protonate this. What do you call it? Carbonyl oxygen, which feels really redundant because in the previous step we deprotonated that. But the reason you have to do that is because if this reaction wasn't heated, this would be the final step. And then when you add heat, it's gonna happen again, basically. So we're gonna reprotonate it. And now this gives oxygen a positive charge. And now we can take that the alpha hydrogen with water. And that's going to create an enol. I got rid of the alcohol in all these. Oopsies. So now where we are, now we can protonate this alcohol we want to leave. So alcohols are not good leaving groups, so we're gonna make it a better leaving group by protonating it. You know, I'm just gonna go across like that. So now we are here. We have a better leaving group, and a better leaving group is going to want to leave. And then to make it leave, we're going to form an alkene right here. Right now we have an alkene adjacent to where we want the alkene. So we can move that alkene to where we actually want it, and that's going to kick off the water. And at the same time, in our product, you'll see we want a carbonyl, so we can also form a carbonyl at the same time. Now we get a positive charge on that oxygen, and the only thing separating us from where we are in the product is deprotonation of that hydrogen. So that's the full mechanism. With heat, it goes all the way to kick off the alcohol and make an alkene. And then without heat, it would be done at this step right here. But by adding heat, that makes us reprotonate the carbonyl once again and continue on to create the alkene. All right, next one, we got to figure out which one hydrogen is more likely to be deprotonated. I think the best way to go about that is show the result of what deprotonating all three of them would look like. Not at the same time, but what would happen if you deprotonated all three. So I'm going to draw the same molecule 3 times. So if we deprotonated the left one, that would look like this, the result. If we deprotonated the middle one, we'd put the negative charge there. And then if we deprotonated the far one, that would put the negative charge there. So to figure out which of the three is going to be deprotonated, we got to ask which of the resulting structures after deprotonation is the most stable. So let's compare them. So this is a primary that can do resonance once. This middle one is a secondary carbanion that can do resonance twice. And then the last one is a secondary carbanion as well that can do resonance once. So I'm sure you can figure out which is the answer then. It's going to be the middle one because it can do resonance twice. That is a lot more stable, making this hydrogen a lot more acidic. So it's going to be second one, and it's because the resulting deprotonation can do resonance twice, which is a lot more stable. All right, next one, we are going to fill in the blanks. So it's an enol reaction. So LDA, what that's going to do is it's going to deprotonate the alpha proton. So if we draw the result of step A, it's going to deprotonate the alpha proton and create our enolate. Then once we have our enolates, we have a nucleophile that can attack our electrophile in the second step. And then the acid quench is going to allow this oxygen to take a hydrogen. So the result of all this is we still have our starting material. We added on this group to the alpha. So one more carbon, and then we have an alcohol attached to that. Next reaction, we are pretty much doing the same thing. The difference is that now we have 2 alpha protons we can take from. So LDA is a bulky base. So because it's a bulky base, it's going to want to take the least sterically hindered alpha proton. So this alpha proton is on a tertiary carbon, where this one is on a primary carbon. So it's going to take the primary alpha hydrogen. So the result of step 1 is going to form an enolate on the least sterically hindered side. And then the rest of the reaction is going to be similar to how we finished the other one. So we're still going to have our starting material. Oh, and I just realized I just showed oxygen attacking that. Should be the alkene. So we're still going to have our starting material, and then on the alpha, we are going to attach the electrophile in the second step. So make sure I draw this right. It's going to look like that. All right, next one. It's the exact same reaction, except instead of a bulky base, we're using a smaller base. And we're also using a weaker base. So we're using a smaller and weaker base. The small part is important for sterics. The weaker part is important in terms of equilibrium, in that it's more stable. The resulting enolate. Okay, so we have two options when we're taking the alpha protons. We could take the left or the right. If we take the left, the resulting enolate is going to look like this. And if we take the right, the resulting enolate is going to look like how it looked in the last one. If I asked you what's the more stable alkene, you would say it's the left one because it's the more substituted alkene. When we have a weaker base, it's going to preferentially form the more stable alkene. And that has to do with equilibrium. If you have questions about that, please let me know. But if you're working with the weaker one, you're going to take the alpha hydrogen that's going to form the more stable enolate. So NaOH is going to take the left alpha hydrogen to form this, and then the rest reaction is going to be the same. So now we're gonna form the carbon-carbon bond on the left side. Like that. All right, last one. We need to synthesize the starting molecule from an aldehyde and ketone. So that's going to be using the enolate reaction since we're in that chapter. And first, let's figure out where's the aldehyde and where's the ketone to start. So here we already have a ketone. If we already have a ketone, this is going to be our starting ketone. Because it wouldn't make sense for that to be the starting aldehyde. And then eventually we're going to have to take, because if that was the starting aldehyde and we eventually need to turn into a ketone, that would mean we'd have to take the hydrogen connected to the carbonyl carbon, which is very hard to take. So a ketone is going to stay a ketone in our reaction. So if this is the ketone, then that must mean that this rest of the molecule was the aldehyde. And the aldehyde was likely right here. But heat caused that alkene to form. So let's draw what the starting ketone would look like, which is going to look like that. And then we're going to need to deprotonate this. So we can use LDA, and we should use LDA because if you notice, let me number the carbons. We form a new bond on carbon 2. So that means that carbon 2's alpha hydrogen was deprotonated. We need to use LDA because LDA, since it's bulky, it's going to take the least sterically hindered hydrogen, which happens to be on carbon 2 instead of on carbon 4, which is on a tertiary carbon. So we need to use LDA. Then we still have to draw the aldehyde. The aldehyde is going to be these carbons here. So let me number them. So we have 3 carbons. And the aldehyde is going to be on carbon 7. And we know that because once carbon 2 attacks carbon 7, this is going to turn into an alcohol. And then with heat, which is the third step, then that's going to, then that alcohol on carbon 7 is going to get eliminated to be an alkene. Alright, so that was the full SI sheet, and text me or email me if you have any questions on anything.